We introduced DeepMesh, auto-regressive artist mesh creation with reinforcement learning. Currently, diffusion-based 3D generation methods have made great progress. For example, Meshi and Ruowen can generate 3D representations through diffusion and then convert them into meshes. However, the meshes from such methods are dense, suffering from poor topology and irregular structures. The chaotic wiring makes them unsuitable for downstream applications. In contrast, artist-created mesh has more optimal topology and are more suitable for downstream applications such as editing and rendering. Therefore, artist-created mesh are preferred and researchers are exploring how to automatically generate them. Previous methods learn to auto-regressively predict mesh vertices and faces, preserving the structure topology. They use a two-stage pipeline. Take mesh knitting as an example. In the first stage, the vertices and faces of a mesh are converted into a discrete token sequence by a tokenizer. In the second stage, an auto-regressive transformer model is trained on this token sequence. During inference, meshes are generated face by face, which helps ensure the mesh's topological structure. However, existing methods face some challenges. First, existing mesh tokenizers are inefficient. Some use the native tokenization, where one triangular face is represented by 9 tokens. AMT and Adrena proposed to reduce the sequence length by half, but the resulting sequences are still long. Although BPT achieves a high compression rate, it requires a vocabulary of over 40,000 at 512 resolution. Additionally, the geometry of current generated results are often incomplete. For example, given an original dense mesh as condition, mesh knitting and BPT both generate incomplete artist-created mesh. Therefore, to address the above challenge, we respectively propose a more efficient mesh tokenizer, and we also introduce a outpost training to enhance the generated result. Similar to BPT, our tokenizer consists of 2 stages. First, the mesh is divided into patches based on topological connectivity. Vertices in each patch are sorted by coordinates, and the vertices of all patches are flattened into a single sequence. Then, the space is divided into 3 hierarchical block levels, and the coordinates are converted into block offset indices. Adjacent vertices with the same offset index are merged. After the above 2 stages, we obtain a discrete token sequence. During pre-training, condition on the point cloud, we train an auto-regressive transformer on the mesh token sequence using an X-token prediction loss. The predicted mesh tokens are decoded into the generated mesh. We then adopt DPO reinforcement training. We first build around 5,000 preference pairs, which are annotated as either chosen or rejected according to 3D geometry metrics and human evaluations, to serve as our DPO dataset. Then, we post-train the model on our constructed mesh pairs using a DPO post-training framework. For more details, we annotate the mesh pairs in the DPO dataset primarily based on geometric completeness, surface details, and wireframe structure. Here we present some examples to illustrate our annotation criteria. We show our experimental results here. Compared with baselines, our method achieves best performance on user studies and 3D geometry metrics. In particular, the model trained with DPO outperforms the pre-trained model in generation quality, validating the effectiveness of post-training. We also verify the efficiency of our mesh tokenizer. In addition to comparing compression rate and vocabulary size across different tokenizers, we measure the training time for one epoch on the same mesh dataset. Furthermore, we conduct an ablation study on datasets with varying mesh phase counts, where our tokenizer consistently achieves the shortest training time under all settings. We further present ablation studies on DPO training. To evaluate the effect of data scaling, we constructed multiple subsets by sampling from DPO dataset for post-training. As shown, larger datasets yield consistently lower validation loss, indicating improved DPO performance. To assess the impact of human annotation, we compare models post-trained on CD-labeled and human-labeled mesh pairs. As shown, Human-labeled dataset leads to lower validation loss and better DPO performance, highlighting the importance of human annotations beyond geometric metrics like CD. We present results on point cloud condition generation and visualize the generation process. Our method DeepMesh outperforms baselines in geometric quality and fine detail preservation, while generating meshes with much more faces. Our method DeepMesh can also generate meshes with diverse appearance given the same point cloud. Thank you for watching. Feel free to visit our project page for more results.